everyone, this is Miss S from Excelsior Charter School, and today we're going to be going over geometry, lessons 2-1 and 2-2 on conditionals and biconditionals. So we do have some vocabulary that we need to get through today, and so we are going to begin with conditionals, hypotheses, and conclusion. Conditional statements always take an if-then form. So here we have a statement. This comes from the practice from this lesson on Canvas. It says all obtuse angles have measures greater than 90. To turn this into a conditional, we need to put it in if-then form, like follows. So there are many ways to do this, but we turn this into if the angle is obtuse, then it measures greater than 90. So this is a conditional statement, and conditionals have two parts. The if part, if the angle is obtuse, which is called the hypothesis, and the then part, then its measures greater than 90, which is the conclusion. So hypotheses always come after if, and conclusions always come after then. And there are several questions on your homework that ask you about hypotheses and conclusions as well. Geometry uses a lot of symbols, and the symbols for conditionals are P and then an arrow which goes to Q, and that's how I write a Q to make sure it doesn't look like a 9. So, but you read this, if P, then Q. Okay, so you can turn any statement into a conditional, but that doesn't necessarily mean that the statement is true. So conditionals can have a truth value of either true or false. So here's a conditional statement from your practice problems. It says, if x equals 12, then 2x minus 5 equals 19. So to figure out if this is true or false, you take this x equals 12 and you plug it in here for x. So 2 times 12 minus 5 will need to equal 19. And when we do the math, 2 times 12 is 24. And 24 minus 5 does equal 19, so this is a true statement. It has a truth value of true. So here's another conditional statement from the practice problems. If the number is an odd integer less than 10, then it is prime. So odd integers less than 10 are 3, 5, 7, and 9. And prime means that they are only divisible by 1 in themselves. So 3 is prime, 5 is prime, 7 is prime. Oh, wait, 9 is not prime because it can also be divided by 3. So this is a false conditional, and 9 is the counterexample to that conditional because 9 proves that conditional false. All right, so we're going to move on to a converse now. And in a converse, you actually switch the hypothesis and the conclusion. So converses can also be true or false. So remember our conditional statement from just a moment ago. If x equals 12, then 2x minus 5 equals 19. And this was true. So now to do the converse, we're going to switch the hypothesis and the conclusion. So our hypothesis here was if x equals 12. And our conclusion was then 2x minus 5 equals 19. So we're going to switch them to get this. If 2x minus 5 equals 19, then x equals 12. So notice how the if and the then stay where they are, but the other information switches places, and that is called the converse. And you have to determine whether or not the converse is true or false. So if 2x minus 5 equals 19, does x equal 12? So to find out, we would add 5 to both sides of this equation and then divide by 2. And what you'll find out is that, yes, that is true. X does equal 12. So the converse is also true. Now, in geometry, again, we like to use symbols. So for a converse, it's if Q, then P, which is the opposite of the conditional statement. Conditionals were if P, then Q. Converse flips it around, if Q, then P. All right, so now we're going to move on to our next vocabulary word, which is a biconditional. So when a conditional and its converse are true, you can combine them to make what's known as a biconditional. And a biconditional will always use the phrase if and only if. So it's not a biconditional if it doesn't have the phrase if and only if. Biconditionals are always true. because both the conditional statement and its converse were true, and that's the only way that you can make a biconditional. So remember from just a moment ago, our conditional, if x equals 12, then 2x minus 5 equals 19. We determined that was true. And then our converse, if 2x minus 5 equals 19, then x equals 12. We also determined to be true. So because both of those were true, we can make the biconditional. So our biconditional here, x equals 12 if and only if 2x minus 5 equals 19. So you take the format of the conditional with the hypothesis first and the conclusion second, but you change it to say instead of if then, it says if and only if. So biconditionals always use if and only if and are always true. And again, because geometry likes symbols, we have our P and we have our Q for biconditionals, but rather than if P then Q, we actually use a double-sided arrow here, and it reads P if and only if Q. All right, so on to our last part here on good definitions. According to our textbook, a good definition uses clearly understood terms, is precise, and is reversible. So according to your practice problems for this lesson, it wants to know whether a cat is an animal with whiskers is a good definition. And the answer is no. And the reason for that is because there are lots of animals with whiskers. So this one is not precise enough to be a good definition. So make sure it holds to all three of those parts, and then you'll be good. Good luck, everybody. I hope you guys do great.